Good evening, everyone. So we are going to be discussing Chapter 8. Chapter 8 is covering universal units. Last week, Chapter 7, we covered the fundamental dimensions and units. And today we're just discussing universal units, which is really just discussing more quantities or units within engineering, right? And so a couple of those units that we're going to discuss, few of them, we'll go into force, weight, density, amount, temperature, pressure. We'll discuss power and energy and a little bit of electrical concepts. First thing we're going to cover is force. So force is what is force? How do you identify force? Well, I like to start when I discuss forces. I always want to discuss Newton's laws. In some textbooks, it describes Newton's laws, which is the form or the foundation of mechanics. Newton's laws is the form with Newton's laws form, the foundation of mechanics. And mechanics deals with three concepts that you should fully understand. Mechanics deals with the study of behavior of objects or structural members when subjected to forces. That's one. Two, in mechanics, by the term behavior, we mean obtaining information about the object's linear and angular rotational displacements, such as velocity, acceleration, linear and angular deformations, and stresses. And then third, the object is defined by its geometric characteristics and material properties. Geometric characteristics provide information such as length, cross-sectional area, and first and second moment of area. Now, we're dealing with Newton's first law. Newton's first law. What is Newton's first law? It is if a given object is at rest, and if there are no unbalanced forces acting on it, the object will remain at rest. So if the object is moving with a constant speed in a certain direction, and if there is no unbalanced forces acting on it, the object will continue to move with its constant speed and in the same direction, right? So if an object is at rest, remain at rest. If an object is moving at a constant pace or speed, it will continue to move at that constant speed if there are no unbalanced forces acting on it. Newton's second law. So for Newton's second law, it is observed, it's basically observed by a formula. And that formula is force is equal to mass times acceleration. Force is equal to mass times acceleration. So if you're looking at the book, Newton observed that as he increased the mass of the object being pushed while keeping the magnitude of the force constant, the object did not move as quickly and had a smaller rate of change of speed. Thus, Newton noticed that there was a direct relationship between the push, which is the force, and the mass of the object being pushed, and the acceleration of the object. He also noticed that there was a different relationship between the direction of the force and the direction of the acceleration. So within your book, there's a video. It's an interesting video. 8.1, I'd advise you to take a look at it because, it's again, like I said, it's interesting, but it breaks down force, breaks down what force is. And so it also breaks down the relationship between acceleration and mass of the object, and gives you the direct correlation between a push and a pull and acceleration and deceleration. So I'd advise you to take a look at that video. All right. So the units of force, right? So you're looking at SI units. The units will be Newton, because Newton discovered this, Newton's second law. And then mass, obviously, to be grams. And so force is equal to 1 Newton. 1 Newton is equal to 1 kilogram, and then acceleration is meters per second squared. So 1 Newton is equal to 1 kilogram meter per second squared. If you've had physics, I know this is just just a review for you. If you've never had physics, which I believe all of you should be either in physics or looking to take physics in the upcoming semester. This is a slide, yeah. So we look at an example. And again, the video really is really good, just discussing this example. Because I'm going to stop sharing, and then I'm going to go to my handy dandy whiteboard. Share that. Give me a minute. Okay. So we have F is equal to mass times acceleration. So if we have some, excuse this little line, we're just going to keep it there. We have some mass, right? And then we have some force acting upon it, right? And we just have the ground. We have the ground, right? And so if you apply this force, and it begins to accelerate at a certain, begins to move, or move at a certain acceleration. And acceleration that it moves about is A. All right. And then it has a mass, so that's essentially going over this box and mass and acceleration. I know that kind of sounds funny, but all I'm just explaining is you apply force to this, just a push, and this is what the guy in the video is really going to be explaining. It's a push, right? Or if you have some type of a rope and you're pulling it back this way. Sorry, it's a pull, right? And what we want to look at is this first example. I'm going to clear all of my drawings. So first example reads, a resupply ship is being designed to use ion engines that run continuously It runs continuously, providing a small but constant acceleration of 0.6 meters per second squared. If the resupply ship has a mass of 30 kilograms, what is the thrust force provided by the engines in units of pounds force? So this is a unit conversion problem, right? So we know it's providing you acceleration is equal to meters per second squared, right? And we know mass is equal to 30 kg. So 30,000 kilograms. He's asking for force, the thrust force, in units lbf. So in SI units, the units for force is Newton. In imperial, or as we discussed last week, US E, USAE, I think. USA, I mean, the United States, American units, USA. The units for forces, pounds, force. All right, now what we need to find is what is the conversion factor for pounds force to Newton, or the conversion factor from newtons to pounds force. And so within your book, you should be able to find that conversion factor. And let's find it. So AES be 1 Newton, 63 pounds. Let's see, sorry. There. So, 63 pounds force, 6 to 1 Newton. And then 1 Newton. Wait, let me see what I'm doing here. No, did that wrong. Sorry. 0.225 pounds force is equal to 1 Newton. All right. Now I know this is really sloppy. It's just, I'm not sure what's going on with my mouse. It just doesn't seem to, when I'm writing, it just doesn't seem to want to come out like, the way I intended to, you know? I could type it, but that just takes too long. And that's not my pencil. Yeah, I have to figure out, draw a line I want to draw. I don't want to erase. Yeah, figure out how to get back to my pencil. Isn't this just lovely? I almost have to just type it in. Like, is that it? Is that my pencil? No, that's a spotlight. That's a check. This is draw. This is interesting. Text. I don't want text. And where is it's behind here. No, that's not it. Maybe it's over here somewhere. Or maybe I got rid of it. Now I'm gonna have to exit out of this just to get back to my pencil. I'm sorry, guys and ladies. This is really, really good. Well, let me exit. And then I'm going to share it again. Share. All right, now it's back. All right, I have my pencil. And so the example from the slide. Back over here. Now we know F is equal to M A. And if you remember, we talked about drawing a free body diagram. Free, which is FBD, a free body diagram when you start all your problems. So it's really unnecessary for this, but we'll just do one anyway, just create a habit. doing so, we have a certain force being applied to a certain mass. We know what the mass is. It's 30,000 kilograms. You know it's accelerating at A, and A is equal to 0.06 meters per second squared. All right, and so it's a free body diagram. All right, so here. And then we know M is equal to 30,000. Kilograms. So we plug 30,000 times 0.06 into this equation. We get F is equal to getting 1,800 newtons. Which we know 1 Newton is equal to 0.225 lb/F. 1 Newton. So if I multiply 0.225 times 1,800 divided by 1 Newton, I will get F is equal to 405 pounds force. And this would it'll get there. All right, moving right along. So we discussed mass, force, and weight. Weight is a force. Honestly, if we were to look at the weight of an object, those of you that don't know, weight is a force. And it's really just covering Newton's second law. But the difference is when you're solving for the force, then you would have to, because it has to be going in a direction, right? So it would be as if the weight would be overcoming the ground. Is it like if you press, or if you want a spring, but you press the ground in with a certain distance, then we would calculate how much weight, which you can still calculate the weight that when you're looking at the normal force acting on an object. But we're not going to be looking into that. But only thing really in that, okay, since in this, just wanted to discuss, so weight is a force, and you would solve B mass times the gravitational pull on the object. And it's just really the same, just the direction. If I were to share my whiteboard again, and I clear all. Clear. There we go. All right, so we have our same box with a certain amount of mass. And this, when I draw, this is so terrible. Try to do this a little neater. There are, so we draw the ground. This is the ground. This is supposed to be the ground. Right, and then you have a box or a mass, showing it as a box, but it's really just an object It has a mass, and it's accelerating at g. And we know that g see if I can erase it and go back to drawing. There it is. You know, the g is the gravitational acceleration, which is 9.8 meters per second squared. All right. And then you have this box that weighs a certain amount of mass. And then that's what you get. Weight is equal to g times mass. Well, that's what that merely is discussing. Don't really want to go too much details in the weight. Weights, it should be pretty self-explanatory. And then even calculating the normal forces on that object. Let's show you. So you have the ground made by normal, which is the last, brings me to Newton's third law, which is Newton's third law is for every action, there's a reaction. So when a force is acting, so when there's a force acting on this object, there's a direct force. When this object, which has a weight on it, which weighs a certain amount, that weight is acting on the ground, and then the ground is reacting to the weight that is being applied to the ground by this object. So there's this weight from the object applied to the ground, and then the ground is applying a normal force directly in the opposite direction on that object. And Newton in the book explains it as in this way. It says, returning to our example of a book resting on a desk as shown. This is a different book, but it says, Newton's third law states that for every action, there exists a reaction. And the forces of action and reaction have the same magnitude and act along the same line, but they have opposite direction. So they'll have the same magnitude. This normal force reacted to the weight of this object. So basically N is equal to W. And the total forces acting on the object, you sum the forces, and that was equal. So if you sum the forces in the Y, we have a normal force acting. So if we did X positive Y, and minus W is equal to sum of the forces is equal to 0. All right, and so your normal force would be equal to W, which is the weight. All right, and so that's how we would look at that and observe that. Now, let's see where we headed next. We covered weight. I think the next thing, I'm not going to do any examples that I want to go into, I believe. Density, not going to really cover density too much, since it is pretty self-explanatory. Density is pretty much the mass of a object over the weight. The mass of an object over the volume of an object. It's the ratio between the mass and volume of the object. That's the density of an object or a substance. Then you have the amount. I think amount is interesting because you're looking at, which is really going into chemistry here, but understanding the difference between amount of a substance and the molecular weight of a substance. And let me share my screen. It's pretty much just going through these slides. Let's see. And so the amount of a substance, the mass is the dimension of how much, and then the amount is the units, which is the dimension of how many, like how many molecules. And so, and then you have the molarity or concentration, which is amount per volume, which is the amount in units equals moles per liter. And so, like I said, a lot of this is chemistry. I'm not going to go into this too heavy. So we're not going to really go into this too much. So a lot of this stuff is, again, pretty self-explanatory. And I'm not going to really quiz you too hard on that. So we're going to jump. There we go. I'm going to jump into temperature. I'm going to jump into temperature because last week we covered a little bit of temperature, and we talked about the units for temperature: Celsius, Fahrenheit, and Kelvin, and Rankine. Describe the difference between absolute and relative temperature scales. And so when you looked at Kelvin and Rankine were the absolute, which means that at zero, absolute zero, the temperature at which molecules have minimal possible motion, the temperature is zero. And then last week we also did some conversions, so we're not going to go with that. Let's see what else we got here. So yeah, temperature is pretty much covered temperature, but pressure. So pressure from described in Pascal's law, right? It is the amount of force being applied to a certain area. All right, so if you think about the units in SI units, the amount of force being applied over an area, it would be newtons per meter, which is described by Pascal, is a Pascal. A Pascal is a Newton per meter squared, because area is meter squared, sorry. So Pascal, it's a Newton per meter squared. And then in imperial or USA, United States, US American engineering system, it would be pounds force, or PSI, pounds force per inch squared. All right. Pounds force per inch squared. So let's see, give you a little bit of literature on this. 1 Pascal is equal to 1 meter squared, and then if you want to convert that to pounds force per inch squared, let's see, what's that conversion? Could have had this handy. Look at them like several different things. Let's see. So we can do a couple examples on this. So a lot of this is just really, we're just going to be converting a lot of this stuff. So we're not going to be doing physics. You guys, you'll be fine there. Not showing it to me in the book. Yep. So 1 psi is equal to 6,894.76 pascals. 6,894.76 pascals. So if we were to look at an example, it asks, what is the systolic pressure limit in units of pascals? So if it gives you high blood pressure is diagnosed when the systolic pressure is greater than 140 millimeters of mercury, and or the diastolic pressure is greater than 90 millimeter of mercury. So it asks, what is the systolic pressure limit in units of pascal? What we know, related equations, P is equal to F over A. We know that it's 1 square meter. And so what we have to do is we got to use the density, since they give us the height of mercury, right? 140 millimeters of mercury, which is the height. And they're asking for the systolic pressure limit in units of pascals. The way we would have to do that is we have to go to my handy dandy whiteboard again. So I'm going to clear this. And we know that P is equal to rho G H. Now, you have to go back to density to figure out what your density of mercury is, or you could just look it up. I'm just gonna say it's roughly, roughly the rho MMA Hg at room temperature it's 13.5 grams per milliliter. Now you have to convert that to kilograms per meter cube, which you would multiply that times 1 kilogram over 1,000 grams times 1 milliliter over 1.0 times 10 -6 meters cubed. That cancels with that. That cancels with that, and you're left with 13,500 kilograms per meter cubed. This is approximate. All right, and so you know rho, you know G is 9.82 meters per second squared. It gave you H, which is 0.140 meters. And plug all of this in, that into that, get approximately 18,559.8 pascals. And obviously, it's going to be approximate based on the density you get from mercury. All right. So that's a pretty good one. Let's see what else we got here. Then you have absolute pressure. So you have total pressure, which total pressure equals the surface pressure times your hydro pressure. Right. And then you have and so, but these will be knowns. So, but what I was looking at was absolute pressure and then gauge pressure. So you have your absolute pressure, your gauge pressure to find that and pull that up. This is in section 8.6. And then there's also a video with that. It's also a pretty cool video. You should watch that. Absolute. So you have P absolute is equal to P gauge plus P atmosphere. Right. It needs to be given. So they'll ask you to solve one or the other. All right. And let's go to, I'm not going to do gas pressure. Gas pressure is pretty simple. It's just instead of liquid, you're looking at gas. So you'll be looking at the ideal gas laws, which PV is the nRT, and a lot of that's plugging, just plugging in. Just plugging in, right? PV is equal to nRT. So you just, they give you R, which is an ideal gas constant. And they'll give you N, and B is the volume, P is the pressure. So a lot of that's just using this equation and plugging in. So I'm not going to go over that too much, but I want to go to energy. Energy. So when it comes to energy, you have work, you have potential energy, kinetic energy, you have thermal energy. So work is the energy of change in distance using force. So like we were saying earlier, when you put against that video, you're pushing something, you're pulling something, just doing work on an object. Now, gravity is not doing work on the object because the object is not moving. And so the object would have to be moving over a distance in order for there to be work. So work would indicate that it is the force times the displacement. And then you have potential energy. So it is the potential, how much energy will be attributed to this object if it were to be released, like a spring. If you were to pull it, it has potential energy. If you were to release the spring, energy would be converted into kinetic energy. And kinetic energy is energy of change of motion, translation, or rotation. And then thermal energy is energy of change in temperature, heating or cooling. All right. So of course, we'll look at some examples. We won't go over each, but more or less it's just truly converting. And so when you look at the units for energy, it'll be a joule. And so when you think about a joule, it is just a Newton, let me see, I think it's a Newton meter per second squared. Because it is that describe, I think it's Newton meter per second squared. So it'd be like force times acceleration, I believe. A joule is that. Let's see. Stuff I should already kind of know this off the top of my head. That's what happens when you're trying to do something and you're extremely tired. So yeah, so it is a Newton per second. So it's a kilogram meter squared per second squared. So kilogram meter squared per second squared. So you know kilogram is a Newton meter rather. Get it together. So you know a Newton is a kilogram meter per second squared. And so it is, I knew that anyway, because I said force over distance. So, and so a joule is a Newton meter. So a kilogram meter per second squared. Sorry about that. So it says, example is, it requires 5650 joules of energy to push an object 15 feet across the floor. And it asks, what was the force applied to the object in units of newtons? So you just divide, you convert 15 feet to newtons, and then you divide the work, the energy being applied to the object, divided by the distance that it was displaced, and then you get 1235.5 newtons. And then lastly, not lastly, but power is a joule per second, and a joule per second. So it is a Newton meter per second. All right, which is a kilogram meters. It's a kilogram meter squared per second cube. So it is the amount of work being done on an object over a period of time. All right, over a period of time. And so the famous equation for this is power is equal to energy over time. And the SI unit for power is a watt. So let's see. And we got efficiency. I'm not going to go over efficiency. There's a few examples. I'm not going to go over the examples. Really just plugging in. Big break. So give me a